Okay, we're going to look at quadratics and rates of change. So what we have here is, and it's a bit small on this page, but you'll notice we have y equals x. This is a linear equation, and y equals x squared. This is actually a quadratic equation, okay? I've condensed it a little so we can do some of our work on the outside. But essentially our quadratic is in blue, okay? So maybe we should try to keep to that. Our quadratic's in blue and our linear equation's in red, okay? And we have some important values. You'll notice for our linear equation, I also have values in a table, and I also have values in a table for the quadratic, okay? So these are the exact equations we're using. These are considered the usually the parent function of something. So y equals x is known to be for the simplest linear equation. Normally we'll write a linear equation where y is equal to mx plus b. In the case of y equals x, we just have y is equal to slope is 1 and the b value is 0. When something is 0, we don't include it, and 1 times x is just x, so we end up back at y equals x. So we have a slope of 1 and the y-intercept is 0, and that kind of makes sense. We have a y-intercept there, and this slope here, if you look, you go over, I'm actually going over 2 in this case, but up 2, it's the same ratio or rate of change as 1 over 1, or 2 over 2, technically the same thing, okay? The y equals, I'm going to do that in blue. The y equals x squared, this is also known as like the simplest quadratic. In this case, it's probably easiest to relate this to the vertex form. And remember, vertex form was y is equal to ax minus h squared plus k. In this case, the a value happens to be 1, the h value happens to be 0, and the k value happens to be 0. And what does that mean? Well, that means our vertex is on the origin, okay? The x value and y value of the vertex. And again, we have that down here. And the a values are stretches and compressions, which we haven't really gone into too much, but it's a standard movement. It's usually known as going over 1, up 1 to start for a quadratic. So you've kind of gone over 1, up 1. And then from there, you can go back to the origin and go over 2, and then you go up 2 squared. So 2 squared is actually the value of 4. So you go over 2, up 4. The same concept is if you were to go 1, 2, 3, we take 3 and square it, and we'd actually go up 9. Where's 3? 3 ends up here. This value is actually 3 and 9, okay? So that's a basic way to draw a standard quadratic if we're doing it freehand. But we're trying to figure out the rates of change. And what's interesting is for linear equations, we'll kind of zoom in here. We're going to look at this linear equation. If you notice, as the x values are changing, and in this case, and we always have to verify this when we are doing rates of change, that the x values are moving by the same amount so that we can start to figure out what type of function or graph we're drawing by the y values of this. And in this case, they're represented by x and x squared. But if you take a look here, the x values are going up by essentially 1 each time, okay? That's really important for us. And that actually is happening on both graphs. They're all going up by 1. So that's our first thing. We can kind of check that off as one of the things we have to make sure. Okay, those are going up by 1. So what are the y values going up by, okay? And in this case, you'll notice this one's just going up by the value of 1 every single time, okay? The way I can do that is I can just subtract each value. But if we get the same value every single time, and this is known as the first difference, okay? And if that is always constant, the value is the same, that means we know we have a linear equation. If you take a look at the quadratics, let's take a look at what they're going. And we'll go from lowest to highest here. This one actually went down by 3, then down by 1, then up by 1, then up by 3. So in our first difference, we did not get like the constant value we got with the linear. So we know this second equation here isn't linear. I'm going to jump into a little space here and move those values. So -3, -1, +1, and +3. What we do then is we take those values, and this is known as the second difference, okay? And we subtract them again. Well, from -3 to -1, that actually went up 2. And then from -1 to +1, that went up 2. And from 1 to 3, that also went up 2. So now we're getting a constant value. So if we get a second difference, think of it as like the second power of a variable, we know we're looking at a quadratic equation. So if we're ever in a scenario where we're looking at a table of values versus the actual graph, by taking a first or second difference, we can figure out what kind of function we're working with. Okay, so let's zoom out a little again. So that's one of the ways we can tell. And if we don't get either of those, it'd be considered not linear or quadratic. There's a whole bunch of other forms. It could be cubic. You could have exponential, which means it's going up by a ratio every single time. But this is a way that we can tell. So a few other hints that we can tell. If you do have the graph here, we'll know our quadratics, and if you take a look, have that U shape to them. If it's a positive a value, it's going upwards, and anything where it's a negative a value will be going downwards. The same concept works for linears, but that has to do with slope. If you have a positive m value, you're going from the bottom left to the top right. If you have a negative m value, you're going from the top left to the bottom right. So just some general ways to tell if something is linear or quadratic, and whether it should open up or down or have a positive or negative slope to it.